All right, so let's talk about how this stuff works here, this elementary matrix stuff. So, what we did before when we were solving systems of equations is we're basically trying to take one of our augmented matrices and do a bunch of row operations so that, hopefully anyway, the left side was the identity matrix, right? That would represent there being one solution. But at any rate, like, we did row operations to put it in reduced row echelon form, right? We can do that more generally and sort of really describe what we're doing here with elementary matrices. So here we have two matrices, A and B. They're m by n matrices. We say that B is row equivalent to A. In fact, there should be a hyphen in here. Matrix B is row equivalent to A if there is a finite number of elementary matrices, E1 through EK, such that what we're basically doing here is we're starting with A, and then we do row operation number 1, row operation number 2, and we keep doing this. And then we'll get to the second to last operation and then the last operation. And after all of those row operations have been done, and again, I want you to, really pay attention to the fact that I'm stacking these on the left. Okay? So after we do the first, then the second, and then, all the remaining row operations, we should get B. Okay? So we'll see this in a little bit. Well, we did some examples above where we, did various row operations. But we'll really see why we're interested in something like this. Okay? So, in order to nail down why we're super interested in being able to make two matrices row equivalent, remember, I'll give you a spoiler here. Remember, the way we find the inverse of a matrix was we write down the matrix and then we adjoin the identity. And then we do row operations until the left side is the identity, right? So what that means is any invertible matrix is row equivalent to the identity matrix. So that's an important fact here, right? Any invertible matrix is row equivalent to the identity. Okay, so where does all this come into play for us? Well, the first thing we need is a theorem here that says elementary matrices are invertible. Right? And we did mention that already, but I want to sort of say how we do that. All right? So let's do just some examples of here's an elementary matrix, here's its inverse. Okay? So this isn't a proof of this theorem, by the way. But yeah. So let's say we take E1 to be, I don't know, what do we want to do? Let's swap row 2 and 3. Right? So this matrix here represents a swap of row 2 and row 3. Right? To get the inverse of this, all we have to do is think, how would we reverse that process we just did? Right? If we swapped row 2 and row 3 in a matrix, how would we undo that? Well, we just swap them back, right? So its inverse is itself, actually. Pretty interesting. All we have to do is just swap row 2 and row 3 again. Right? If we swap them once, just swapping them again will put them back in order. Great. Fantastic. So that tells us how we can undo the row swapping, what the inverse of those look like. All right. What if, say, our second elementary operation would be let's multiply row 3 by 4. Let's say. Right? So here, our row operation was 4 times row 3 goes to row 3. How do we get the inverse of this? Well, again, it's just a row operation, so think of what could you do to undo what we just did? Well, if we just multiplied a row by 4, then to undo that, we would divide the row by 4. Right? Does that make sense? So, over here, we want to divide row 3 by 4. So, it'd look like this. That's the inverse. Right, hopefully this makes sense. It's hopefully not too bad. Right? Again, so these inverses, like, we can just sort of logically think through, what we're actually doing here. We know what this elementary matrix does, and we just think about how do we undo it. All right, so let's do this one more time, because there's one more type of elementary matrix. Oh, that E3. Let's see. Row 1 hasn't got any love yet, so let's do row 2. Row 2 plus 7 row 1 goes to row 2. Right? Let's do that as our row operation. Right, so row 1 won't change up here. Row 2 will be 7, 1, 0, and then we'll 0, 0, 1. Right? So, how do we invert this? Right? How do we undo adding 7 copies of row 1? Well, if we added 7 copies of row 1, then we can undo that by subtracting 7 copies of row 1. Right? The operation to undo that should be R2 minus 7R1 goes to R2. Does that make sense? So, that... change colors here. Come on. 1, 0, 0. Minus 7, 1, 0. 0, 0, 1. There we go. That'll undo it. So pretty interesting stuff, I think, how this works out. One thing I might suggest if you're unconvinced of any of these, in fact, maybe it's a good idea to try this anyway, just to sort of show yourself that our reasoning is fine. Multiply these pairs of matrices, so E1 and E1 inverse, E2, E2 inverse, E3 and E3 inverse. And you can really see that, yeah, these actually are inverses of each other. Right? So, now that we know how we can invert elementary matrices, in the next video we'll talk about why we really want to do that.